Greetings and welcome, friends. Section 2.5, Compound Inequalities. You thought one inequality was complicated. Well, what if there's two at a time, simultaneously happening? Yeah, that's pretty much the idea. I'll show you how it works. This is going to be great. By the end of the video, we'll know what this is. A compound inequality is an inequality formed by joining two inequalities with the word and or the word or. So joining two inequalities and then having a logical combination between them. All right, so over here on the left, I've got two inequalities. I've got x is greater than or equal to 2, would have been closed circle. That's weird, like this graph is not helpful for the number anyway. But it'd be a closed circle at 2, and oh, I see they've got the numbers down here. That's kind of weird though. Shaded to the right, I've got x is less than 5, would have been an open circle at 5, shaded to the left. Now, if I use the and logic and combine those two into a single inequality, what I'm saying is which numbers are greater than or equal to 2 and less than 5 at the same time. All right, so let's consider some of these numbers. So for instance, the number 3 is greater than or equal to 2, and it's less than 5, therefore it's on my common number line between the two of those things. All right, let's look at this. How about 2 itself? 2 is greater than or equal to 2, and it's less than 5, so therefore it shows up on the common number line. Now check this out. Okay, here we go. What about 6? Here's the point 6, okay? 6 is greater than or equal to 2. Cha-ching. But it is not less than 5. Therefore, notice it is not on the number line here. Even though it was true for one of those inequalities, it was not true for both of them, so we don't count it. That's how the and logic works, okay? It's got to be true for both. So 6 is not on that number line. Also notice this, say positive 1. Hey, that was true for this. X is less than 5, 1 is less than 5, that's true. But it's not greater than or equal to 2, therefore it didn't show up on the compound inequality when I used an and operator between them. Now check this out. If I have an and operator, what my inequality ends up looking like is a number line that's shaded in between, okay? In between. All the points, which there are still infinitely many points in between these, but all the points in between those two values, and in this case it includes 2, it doesn't include 5. All right, instead of just writing this as and, we actually, as mathematicians, as efficiently lazy people, we have a shorter way of writing it. Where I actually write this, I call writing this from right from least to greatest. Least to greatest. And you can actually have multiple inequalities in a single inequality. That's so crazy. But look it. So according to my graph, the smallest number I have is 2. Then I've got all of my solutions, which we call x, and then the biggest value I have occurs at 5. So from least to greatest, it's 2, then x's, then 5. And then I would write all my inequalities in less than form, least form, right? Less than. So this 2 is less than or equal to x is less than 5 is actually how you would even read that out loud. Okay, so that's how you can write it from least to greatest form, rather than just throwing an and in between them. That's okay when you're solving, but once you're done, let's simplify it to this compound form. All right, and so the graph of a compound inequality with and is the intersection or the common points, okay, of the graphs of the inequalities. The graph shows numbers that are solutions of both inequalities. So and means it's got to be true for both of the originals. Now the or operator, okay, is going to be a little different. The graph of a compound inequality with or is the union, that means the combination, All right, every solution that worked for either of them works now for this one. All right, so the graph shows the numbers that are solutions of either inequality. Okay, so notice this over here. Y is less than or equal to -2. All right, there's those closed circles shaded to the left. Y is greater than 1, open circle shaded to the right. If I throw the OR operator in between them, that means both of these graphs work simultaneously. And notice that no point in this graph was actually a solution of both of those at the same time. Okay, it was only a solution of one or, there's my word, the other. Okay, so it was just one or the other. It's a combination. You add the graphs, you unite the graphs together. There is no requirement for both of them to be true simultaneously. In fact, none of those points will make both of my original statements true, just one at a time. So let's do an example here. Example 1. All right, write each sentence as an inequality. Graph the inequality. So let's see, here we've got a number x is greater than -8. Let's see, I see the word and, less than or equal to 4. So I could say x is greater than -8 and x is less than or equal to 4. Let's now write this as a compound inequality. What's the smallest value here? -8. So I'm going to write it -8. Then my x's will be in between because it's an and. So I'll have -8, then x, and then the biggest value I'll have is 4. And now I'll write it with all less than signs. Notice this is currently a greater than sign. I'm going to have to flip it around to account for the fact that -8 is less than x, where x is bigger than -8. And then I've got the less than or equal sign for the 4. So that's how I would write that inequality. If I wanted to graph it, let's see, we usually use the white for the number line, don't we there? And I didn't use my straight edge, but I'm content with what I've got. So let's see, so I'll have 0, we'd have like 4 hanging out here. -8 would be twice as far away from 0 as 4 was. And my solutions, let's see, it's an open circle at -8, a closed circle at 4, and shaded everybody in between. Everybody in between. Here we go. All right, there we go. So there's my graph for that problem. Let's look at question B. It says, I guess, yeah, question B. A number y is at most 0 or at least 2, or operator. That means these are going to be pointing away from each other. They're going to be in contradiction to each other. None of them will simultaneously be true, but I'm fine with either of them being true at a time. So I'm going to have y is at most 0. So y is at most 0. That means it's got to be less than or equal to 0. And then I'll throw my or operator. Actually, sometimes I even like the capital OR. It just looks cool, even though I do lowercase for and. I don't know why I do that. I like the OR. Or at least 2. So that means it can be 2 or greater than that. Okay, so here's how I could write that inequality. And if I want to graph that inequality, let's see, 0 and 2. And let's graph our solution set. So less than or equal to 0, closed circle at 0, and shade it to the left. Okay, and then let's see, x is, I wrote x instead of y, guys. Oh, man. Wah, wah, wah. There we go, that's better. Or y is greater than or equal to 2, closed circle, shaded to the right. So these are compound inequalities because we have multiple inequalities in a single problem. Our solution sets are a little bit more interesting as a result than just a regular old inequality, right? We've got all sorts of things happening at the same time. So let's take a look at another example here. Ooh, I love it. This is so great. Man, these problems are the best. Here we go. Things just got interesting, friends. What? This is like some sort of, what do they call them, a Mexican standoff when you got multiple people pointing guns at each other and you never know who's gonna shoot first. Here we go. We've got three separate sides, quote unquote, of this inequality. What? What? How do I solve? That's crazy. Three separate sides of the inequality, guys? Are you seeing this? Are you seeing this? So, all right. If I want to solve inequalities, okay, that are compound inequalities with this and operator that are already written in less than form, notice, right? I've got separate inequalities. I pretend that it's just a regular inequality, okay? If that wasn't there, how would I have gotten x by itself? What would I have done to get x by itself? I would have added 2 to both sides. Now what I'm going to do is add 2 to all sides. Everybody gets plus 2. So -4 plus 2, signs are different. I subtract them, I get 2. Keep the sign of the more influential. Inequalities still pointing in the same direction. X is now by itself, and let's see, is less than 3 plus 2 is 5. Okay? So it turns out I can add 2 to all 3 sides. How crazy is that? I mean, nothing too new. It's just got this new little piece to it. It's just like, but it's all the same skills. Okay, how about over here? I want to get x by itself. I've got 3 sides, so to speak, of this inequality. X is being multiplied by -2 and added by 1. Which one should I move first, the -2 or the 1? The 1, right? So I'm going to subtract 1 from both sides. Nope, all 3 sides. Okay, everybody's subtracted by 1. So here it gets more negative. So -4 is less than -2x is less than or equal to 8. And now how do I deal with that multiplying by -2? What's the inverse of multiplication? Inverse of multiplication? Division. And I'm dividing all 3 sides by -2. So I'm going to have +2. I'm going to have x, and I'm going to have -4. And check this out. I divided by a negative, so I flip those inequalities. What? Right? Now, x is solved, but I want to write this from least to greatest, so I'm actually going to flip the entire thing one more time. I'm going to have -4, I'm going to have x over here, and then 2 over there, and I'll have to flip the entire thing. So now this inequality is going to be over here and flipped. This inequality will be over here and flipped. That one's a little bit trickier there. Kind of those things are getting crazy here. Let's see if I, let's see, 0 degree angle. Let's graph these. And over here, so I will have -2. I'll have 0, and 5 is further than 2 is from 0, so that's roughly my scale there. Here I'll have -4. I'll have 0, and 2 is closer to 0 than 4 should be, so I should represent that on my scale. And let's see, are these going to be shaded in between or shaded away from each other? These are and problems. X is in the middle. X is in the middle, so my solutions will be in the middle. They'll be shaded in between. So let's see, -2 is less than x, so open circle at 2, which is less than 5. Open circle at 5. X is in the middle. Here we go. Monkey in the middle, right there. That good old x. And here we go. -4 is less than or equal, so that's a closed circle. Shade that in. And open circle at 2. And x is in the middle of the inequality, so x is in the middle for the solutions on the graph. Right. We're good. So, interesting problem, little bit. Here, how about this one? Let's do an OR inequality, OR compound. All right, this one's going to be a little bit more interesting, a little bit more interesting. Yes. So here I've got my OR operator. I've got two separate inequalities, and I'm just going to solve them both individually and just kind of keep my OR logic in play here. So let's see. I'll do this quick. Add 5, add 5. Over here I would have added 1, added 1. I'm just trying to minimize swapping colors as much. Let's see, 3y is less than negative 3. Over here I'd have 2y is greater than 6. Divide step, div 3, both sides. Over here, it's div 2. And I will get y is less than negative 1. Oh wait, do I have to flip the sign? Do I have to flip that sign? No. Ooh, tricky question. I divided by positive even though there was a negative in that fraction. I divided by a positive, don't have to flip it. And over here, div both sides by 2, I'll get y is greater than 3. And let's throw this OR in the mix. Bam! And box it. And let's draw our number line here. Okay, here we go. So let's plot our interesting points. 1, negative 1 is interesting to us. 0 always should be thrown in the mix. And 3, I kind of spaced it out as though, right, it's set up there. So when I graph this, y is less than negative 1. Less than negative 1 would be shaded this way, open circle. And greater than 3, open circle, shaded this way. So my solutions are all of the points to the left or to the right of negative 1 and 3. And nothing in between them, or not including them themselves, okay? Not including themselves, like so. All right, let's see if I can get some of this example done before the bell. We've still got time. And here we go. Last example. Electrical devices should operate effectively within a specified temperature range. Outside the temperature range, the device may fail. Wow, it's terrifying. Terrifying. Let's see, write and solve a compound inequality that represents the possible operating temperatures in degrees of the smartphone. Uh-oh, guys, you know what? I think I messed up here. I didn't copy the picture of the graph of the smartphone. Uh-oh. Okay, all right, but I've got that information. They told us the additional information was it can operate between 0 degrees Celsius and 35 degrees Celsius. Okay? 0 and 35 Celsius. So let's write this inequality as far as that goes. So my variable, I could say C is temp in Celsius. Nope, Celsius that the phone operates in. All right, we don't want it too hot or too cold. So let's write our inequality, compound inequality. I'm saying it's going to be somewhere between 0 and 35. So I'll say 0 is less than or equal to C is less than or equal to 35. Okay? That's my inequality. Now they just said, what about in Fahrenheit? All right, you guys, I'll see you later. I'm going to keep doing this problem. Well, if I want Fahrenheit, Celsius is equal to 5/9 times the Fahrenheit minus 32. And so what I'm going to do is actually take this and plug it in here for C, making this problem slightly more interesting. 0 is less than or equal to 5/9 Fahrenheit minus 32, which is less than or equal to 35. And so if I solve for F, I'll actually get my temperature range in Fahrenheit. Okay, so let's solve for F. So I'm going to multiply both sides by 9/5. Wait, not just both sides, all 3 sides. All 3 sides. And let's see, so 9/5 times 0 is 0, less than or equal to, here the 9/5 and 5/9 cancel out. I'll get F minus 32. Sure, I could have distributed that, but I think in this case it was easier dealing with that fraction first. 35 divided by 5 is 7. 7 times 9 is 63. And now I would just have to add 32 to both sides to get F by itself. Yep. Or all 3 sides in this case. So let's see. So 32 is less than or equal to F is less than or equal to 95 is the range of solutions. Let's see. What did their question actually ask? They said, find the possible operating temperatures in Fahrenheit of the smartphone. So the phone works between 32 degrees and 95 degrees Fahrenheit. Okay, let's see what part B was real quick. Describe one situation in which the surrounding temperature could be below the operating range and one in which it could be above. So let's see. So if it's freezing outside, if you leave your phone in your car overnight and it went below 32, your phone might not be happy as much. And over 95 degrees, if it's really hot outside, you leave your phone in the sun, right? Something like that, that could bring it above that temperature. All right, well, thank you so much for watching, Internet friends. Hope you have a great day. And be careful with your cell phone use.